Dear students, Assalamu alaikum. I am loading two videos to cover my lectures for this week, as I am busy on a domestic involvement. But after watching these videos, if you have any problems, we will discuss it when we will meet next week face to face. Okay, today I will talk about this chapter from Ali Umar, chapter number 8, which is the dielectric and optical properties of solids. So after establishing the band theory of solids in our previous semester, we are now able to discuss the properties of solids. So let us first discuss the dielectric properties. Okay, in this chapter we shall discuss dielectric and optical properties of solids and other phases of matters. These properties span an enormous range of frequencies from the static to the ultraviolet region, and provide valuable information on the physical properties as well as the structure of matter. So after an elementary review, we shall relate the dielectric constant to the polarization properties of the molecules constituting a given substance. Then we shall consider the various sources of molecular polarization, dipolar, ionic, and electronic contributions. Finally, we shall consider two important properties, piezoelectricity and ferroelectricity. Both are related to ionic polarizability. Okay, now review of basic formulas. Now these are the basic formulas in which we will introduce various types of fields. Let us review some of the basic formulas which will be useful in the following sections. A concept most important in this chapter is that the electric dipole and its moment. Think of an electric dipole as an entity composed of two opposite charges of equal magnitudes q and minus q, as in figure 8.1. So here are two charges, equal charges in magnitude, minus q and plus q, separated by displacement d. The moment of this dipole is defined by this equation. Moment is represented by the vector p, small p, which is equal to q and into the displacement, where d is the vector distance from the negative to the positive charge. The electric moment is therefore equal to one of the charges times the distance between them. In your previous classes, you may have evaluated the electric field due to a dipole like this, and equation 8.2 is the expression for the electric field due to at a point P, which is distant r from this dipole, from the center of this dipole, and the expression you may have derived in your previous classes is given by equation 8.2, that electric field due to this dipole is given by 1 over 4 pi epsilon naught 3 p dot r into r minus r square p over r phi, which gives the field in terms of r, the vector joining the dipole to the field point, and the moment p. In deriving this expression, we have assumed that the distance small r is much larger than the displacement. That is, expression 8.2 is valid only at points far from the dipole itself. In atoms and molecules, this condition is well satisfied, since d, being of the order of an atomic diameter, is very small indeed. Okay. When a dipole is placed in an external field, it interacts with the field. The field exerts a torque on the dipole, which is given by equation 8.3. Tau is equal to the cross product of P and the electric field, where E is the applied field. The magnitude of this torque is P E sine theta, where theta is the angle between the directions of the field and the moment, and the direction of tau is such that it tends to bring the dipole into alignment with the field. This tendency towards alignment is a very important property, and one which we shall encounter repeatedly in subsequent discussions. So here is the diagram 8.2. Here is this dipole, and the electric field is applied in this direction, and this electric field exerts a force QE on the positive charge and minus QE on the negative charge, and obviously due to these two parallel and opposite forces at two ends, the dipole will rotate, and the torque is given by expression 8.3. Another and equivalent way of expressing the interaction of the dipole with the field is in terms of the potential energy. So potential energy associated with this torque is given by V is equal to minus P dot E, which is minus P E cos theta, equation 8.4, which is the potential energy of the dipole. We can see that the energy depends on theta, this angle, the angle of orientation, and varies between minus PE when the dipole is aligned with the field and theta is 0, and plus PE when the dipole is opposite to the field and theta is 180 degrees. Because the energy is least when the dipole is parallel to the field, that is minus PE, it follows that this is the most favored orientation, that is the dipole tends to align itself with the field. This is of course the same conclusion reached above on the basis of torque consideration. So in discussing dielectric materials, we usually talk about polarization P of the material, which is defined as the dipole moment per unit volume. If the number of molecules per unit volume is capital N, and if each has a moment P, it follows that the polarization is given by capital P is equal to N into P, equation 8.5, where we have assumed that all the molecular moments lie in the same direction. When a medium is polarized, its electromagnetic properties change. This is expressed through the well-known equation, and we introduce here capital D, which is known as the electric displacement vector, and this is given by epsilon naught into E plus P, where epsilon naught is the permittivity of the free space, and if this dipole is placed in a certain medium, then we will have epsilon, which will be the permittivity of that particular medium. It is also well known that the displacement vector capital D depends only on the external sources producing the external field, and is completely unaffected by the polarization of the medium. It follows that the external field E naught, that is the field outside the dielectric, satisfies this equation, that D is equal to epsilon naught into E naught. So when we compare this equation with equation 8.6, we find that E is equal to E naught minus 1 over epsilon naught into P, equation 8.8, showing that the effect of polarization is to modify the field inside the medium. In general, the results is a reduction of the field. Equation 8.6 is usually written in this form, equation 8.9, where the relative dielectric constant introduced here is given by epsilon r is equal to epsilon over epsilon naught. Epsilon is the permittivity of that medium and epsilon naught is the electric permittivity of free space or air. All the dielectric and optical characteristics of the substance are contained in this constant. So this is a very important parameter known as the dielectric constant, and indeed much of this chapter is concerned with evaluating it under a variety of circumstances. Thus it follows that we can gain much information about a medium by measuring its dielectric constant. So dielectric constant is an important parameter of a dielectric medium. From this point on, we shall refer to the relative dielectric constant epsilon r as simply the dielectric constant, and this is given by equation epsilon is equal to epsilon naught into epsilon r. Now figure 8.3 over here, this represents shows a simple procedure for measuring dielectric constant. That how can we measure the dielectric constant of a given medium? The plates of a capacitor are connected to a battery which charges the plates. When there is no dielectric inside the capacitor, the electric field produced by the charges is E naught, which can be determined by measuring the potential difference V naught across the capacitor and using this expression, equation 8.11, where L is the distance between these two plates. So these are the two plates and this dielectric medium is not there, and the equation we have mentioned here is the electric field given by V naught over L between these plates. If a dielectric slab is now inserted between the plates, the field E naught induces the polarization of the medium that is lining up of the dipole moments along the field, which in turn modifies the field to a new value E. This new field can be determined by measuring the new potential difference V by a voltmeter and using the relation equation 8.12. The dielectric constant is given in terms of the field E naught and E by this relation. So this is one expression to calculate the dielectric constant or relative permittivity, as can be seen by comparing equation 8.9 with equation 8.10. It follows therefore that the relative permittivity or dielectric constant epsilon r is equal to E naught over V, where we used equations 8.11 and 8.2. We can thus obtain the dielectric constant by measuring the potential differences across the capacitor with and without the presence of the dielectric and taking their ratio. Okay. Figure 8.4 here shows why the polarization of the medium reduces the electric field. The effect of the polarization produces net polarization charges situated at the faces of the dielectric, a positive charge on the right and a negative charge on the left. Okay, so you can go through the rest of this paragraph. But let me move on to the next topic. The dielectric constant, as we said, is a very important parameter, and we will correlate this with the polarizability of the medium, and we will introduce the local field. Since the polarization of a medium, that is the alignment of the molecular moment, is produced by the field, it is plausible to assume that the molecular moment is proportional to the field. Thus we write P is equal to epsilon alpha E, where alpha is the proportionality constant and is known as the polarizability of the molecule. So equation 8.15 is the defining equation for alpha, which is the polarizability of a molecule. This expression 8.15 is expected to hold good except in circumstances in which the field becomes very large, in which case other terms must be added to equation 8.15 to form what is in effect a Taylor series expansion of P in terms of E. Equation 8.15 may be regarded as the first term in this expression. Okay, so the polarization capital P is now defined by this expression, equation 8.16, equal to N into alpha into E, which when substituted in equation 8.6 yields the displacement vector equal to this expression given by equation 8.17. Comparing this result with equation 8.9, one finds that the relative permittivity, or epsilon r, is equal to 1 plus n alpha over epsilon naught, equation 8.18, giving the dielectric constant in terms of the polarizability. So this is the equation which correlates the dielectric constant epsilon r with the polarizability, that is alpha. This is a useful result in that it expresses the macroscopic quantity. Now this epsilon r is the macroscopic quantity and alpha is the microscopic quantity. So this equation is useful as it is relating a macroscopic property with the microscopic property. Next we define the electric susceptibility chi of a medium, and the defining equation is given by equation 8.19, that capital P, the total polarization, is equal to epsilon naught chi into E. This is not necessarily true at higher frequencies. See section 8.9. Okay, which relates the polarization to the field. So this equation 8.20, chi is equal to n alpha over epsilon naught, and the next equation 8.21 correlates the dielectric constant with the with chi. Okay, this is thus the departure of the dielectric constant from unity. The value for vacuum is equal to the electrical susceptibility. Chi is called the electrical susceptibility. Okay, so equation 8.18 may also be written in terms of the density of medium by noting that n is equal to rho Na over m, where rho is the density, m is the molecular mass, and Na is the Avogadro's number. So when we combine these equations, we get equation 8.22, that the epsilon r is 1 plus rho Na over epsilon naught into capital N alpha. This expression indicating that epsilon r increases linearly with the density holds in gases in which density can be conveniently varied over a wide range. This fact lends support to the argument used in the derivation of equation 8.19 and in particular to equation 8.15. Okay, so go through the rest of this page and come to the equations 8.23, 8.24. Now 8.24 is the here is the diagram which gives us various types of electric fields. So one is this externally applied field epsilon naught, and E1 is the field produced due to the polarization of the medium, and then there is a field E2 which is the internal electric field as shown here. So let us now evaluate the various fields, and these are the expressions 8.25, equations 8.26, equation 8.27, which gives us expressions for the various types of fields, and the total field, local field, is defined by equation 8.24 as the sum of all these fields as I explained before. Okay, so let me you will complete this topic going through the rest of the pages up to equations 8.34. Okay, so let me stop here, and now this is the first video, and to cover the one lecture, and in the next video we will move from this point onwards and I will present the second video, and that will cover your 2 lectures. Okay, thank you very much.